Okay, so we were discussing about closure. Yeah? So can anyone recall the definition of closure of a set? सरोज चंद्रा, सरोज, क्या आप मुझे सुन पा रही हैं? नेहा, हेलो नेहा, हेलो, क्या हो गया यार? आप सुन पा रही मुझे? अनुराग?
यस सर।
रिकॉल करेंगे डेफिनेशन क्लोजर की?
सर अगर हम कोई भी क्लोज सेट लेते हैं उनका इंटरसेक्शन, अगर कोई क्लोज सेट ए लेते हैं उनका इंटरसेक्शन लेते हैं, जो सबसे छोटा सेट मिलता है उसको हम क्लोजर ऑफ अ सेट कहते हैं।
आप बहुत कुछ बता दिया आपने, लेकिन इसको थोड़ा और ठीक करते हैं। आपने क्या बोला पहले बताइए।
सर अगर हम कोई एक सेट ए लेते हैं,
पहले टोपोलॉजिकल स्पेस लो। ओके, एक्स टाउ एक टोपोलॉजिकल स्पेस है, और क्या लिया इसके बाद?
सर एक कोई सेट हमने ए लिया,
ए एक सबसेट है एक्स का। ओके,
यस सर।
देन व्हाट इज क्लोजर ऑफ ए?
सर क्लोजर ऑफ ए इज द स्मॉलेस्ट क्लोज सेट कंटेनिंग ए, या इंटरसेक्शन ऑफ ऑल क्लोज सेट
smallest closed set containing a is the closure. Okay, closure of, और आप इसको कहते हैं intersections of all closed sets containing ए को कंटेन करने वाले सारे क्लोज सेट का इंटरसेक्शन ले लो। ये दोनों सेम होते हैं, हमने देखा था। ओके, so let us see closure in a subspace. Okay, अभी क्या है, हमारे पास एक टोपोलॉजिकल स्पेस है, y एक सब स्पेस है x का, इसका मतलब y पास सब स्पेस टोपोलॉजी है। ओके, you all know in a subspace topology every open set of y are g equal to f intersection y, where f is in tau. Okay, so you know this. So this is how we define subspace topology. Now we have a subset of y. So this A is a subset of y and y is subset of x. So you have two things. Okay, A as a subset of x, A as a subset of y. Okay, so you know the definition of closure of A as a subset of x. You know this. So how do we define closure of A as a subset of y? This is new task. Okay, so let us do this. How do we define? So can anyone guess how could we define this? कोई guess कर सकता है कि कैसे define कर पाएंगे हम? हाँ, okay, so our next theorem is a result where we see closure in subspace topology. Okay, let x tau be a topological space and y be a subspace of x. Okay, this means we are taking tau y, the tau y on y, okay? Topology tau y on y. Let A be a subset of y, then closure of A in y. Closure of A in y is nothing but closure of A in x intersection y. Okay, let us see a proof of this. So by definition, so what we do, we will prove two things. But first we will prove that closure of the y, so closure of A in y is a subset of closure of A in x intersection y, and second part, closure of A in x is subset of closure oh, intersection y. So these two things we will. So these two implies they are equal. Okay. So this is our claim. Okay. By definition, what is closure of A in X? This is closed set. This is a closed set in X. Okay? Closed set in X which contains A. Okay. Which contains A. So you all know that closed sets in Y are of this form, are of the form, say E intersection Y, where E is a closed set in X. Okay. So if this set closure of A in X is closed set in X, then using this observation, what we get, closure of A in X intersection Y is closed in Y. And you know, this set contains A. Okay, why? Because here closure of A in X contains A and Y already contains A. Therefore, A is contained in closure of X intersection Y. Is this clear to everyone? This implies, so since closure of Y in A, it would be the smallest closed set in Y containing A. So this is a closed set in Y containing A, and this
Sir,
would
the
be
screen is
smallest.
paused.
Hello? हेलो, किसी ने कुछ बोला?
Yes, sir, the
आप
screen
लोगों
is
को मेरी
paused.
स्क्रीन नहीं दिखाई, अभी भी नहीं दिखाई दे रही? स्क्रीन शो नहीं हो रही क्या?
सर रुकी हुई है सर, paused है.
यस सर, मेरे साथ भी दिक्कत हो।
नो सर,
अभी ठीक है?
आप तो शो ही नहीं हो रही है। आप सही है।
ठीक है ना? Okay. So let us recall what we have done. So we started from the definition of closure of A in X. It is a closed set containing X. In fact, it is the smallest closed set. Okay. Now you know closed set in Y are of this form, where this E is closed in X. So when you take intersection of Y and closure of A in X, this set will be closed in Y and it will contain A. Okay. Since closure of A in Y is the smallest closed set containing A, we get this inclusion. Okay. Again, on the other hand, what we know is, so one part we have proven. Okay, this part we have done. This part is done. Now next part, on the other hand, what we know is closure of y in A is, this is closed in y. Okay. Now let E, so we have to prove this one is the smallest closed set containing A. Okay. So let me write it. Is closed in y containing A. And in fact, it is the smallest subset. Okay. Now what you do, you take closed set, any closed set E in y, okay, closed in y containing A. Containing A. E is closed in y and E contains A. Now you prove that this closure YA is contained in E. Okay. So this is what we will prove. So what you do, this is by definition, this is true by definition of closure. So far it is okay, because closure of A in Y is the smallest subset. Now you know, when this E is closed in Y, this means it is of this form, F intersection Y, where this F is closed in X. Okay, correct? And F contains A. Okay, so from here what you get, this, since this F is closed in X and it contains in A, this implies closure of X, so closure of A in X contained in X. So take intersection with Y. So this intersects with Y, this intersects with Y. Okay, this part is nothing but E. Okay, so what you get, you took any arbitrary closed set in Y, any arbitrary closed set in Y which contains A, and you are getting that this arbitrary set contains this set. This means this is the smallest set. Okay, this means this is the smallest set. So what you get, so whatever you have observed so far, let me write this. You have proven that if the closed subset of Y containing A also contains Y intersection closure of A in X. Okay, but you know, closure of A in Y is closed and contains A. So by this observation, what you get is, you get Y intersection closure of XA is contained in closure A in Y. Now we have proven another part. So this part, okay, this implies these two things are equal. So hence closure of A in Y is same as closure of X intersection Y. Any doubt?
No, sir.
Okay. So let me give you another theorem. So we will see some results about this closure in subspace topology. We will see some examples. Okay. Let A be a subset of a topological space. Okay. X. Then X in closure of A in X if and only if every open set containing X intersects with A. Okay, what does it mean by intersect with A? So any set U intersect with A means A intersect U intersection A is non-empty. This is what intersect means. Okay. Let us prove this result. So what we will do, we will prove this result by contrapositive thing. Okay, what is contrapositive? So we will, so this is of this form P if and only Q. Okay, what we will prove not P if and only if not Q. Okay, correct? So we will, so what is contrapositive of this left hand side? X in closure of X, closure of A in X. Contrapositive of this is X not in closure of A in X. Okay. And what is contrapositive of this part? That every set, every open set containing X intersects with A. So whenever, when you find contrapositive of such thing, this every will replaced by there exists or some open set. Okay, there exists at least one. Okay? So we will prove this if and only if there exists at least one open set. Okay, containing X does not intersect with it. So call it U. Open set U containing X such that U intersection A is empty. Okay, so this is what we will prove. Any doubt? किसी को कोई दिक्कत है यहाँ पर?
No, sir.
Okay. So now we assume that X not in this, and we will show that there exists at least one open set such that which is disjoint from A. Okay. So this is very easy. How? Okay. So let us. So suppose this is X. Here you have A. Okay. You are saying X is not in closure of. So closure of A, suppose this part is closure of A, this green part, okay, this is say closure of A. Suppose this is closure of A, because closure of A contains A, okay. Suppose this is this, and you are saying that this X is not in closure of A. So this means X is somewhere here, okay, outside this closure of it. So this means X belongs to X minus closure XA. Okay, can anyone tell me what kind of set this is? Is this open? Is this closed? Or is this both open and closed? Arpit, Raj?
Yes, sir. It will be open.
Arpit, Raj?
Yes, sir.
Arpit, what kind of set this is?
Sir, it will be an open set.
Why?
Because it is the x minus closure of A, means it is the complement of closure of A.
Then why are you saying this is open?
And closure of A is itself is a closed set, and a
So
set
because this is
according
complement
to
of a closed
definition,
set.
a set complement is open.
Yeah. Okay, very good. So because this is because this closure was closed set, its complement will be open. Okay. So this X belongs to this set, this is open. X minus closure X A is open. Do you see, we wanted to prove existence of an open set containing X such that U intersection A is empty. So from here, you see this X minus closure of X A intersection A, this is an empty set. Why? Okay, let us see the figure. So this part was closure. Okay, this part was the closure. So closure of A and X minus closure A, they are disjoint because this is complement of this. Okay, they are disjoint. And A is sitting inside closure. Therefore, so let me make it via this color. So this I am drawing X minus closure of A. Okay, and you see this is disjoint from A. So we have proven whatever we wanted to prove. Take u equal to X minus closure of A in X. This is open and U intersection A is empty. So this is what you wanted to prove. Okay, any doubt? किसी को कोई प्रॉब्लम है इसमें? प्रतिभा रजावत? प्रतिभा?
Yes, sir.
ना कोई प्रॉब्लम?
Sir.
हाँ?
Sir.
Okay, now we assume this part. Okay, we now assume this part. Means there exists at least one open set U, okay, such that containing X such that U intersection A is empty set. We assume this and we will prove that X is not in closure of. Okay. Conversely, assume that there exists an open set U containing X such that U intersection A is empty. Okay. Since U contains X and U is open, so this means, okay, so let me draw this figure. Okay, draw the figure. So suppose this is your X, this whole thing was X. Now we have two sets U and A. So say this is U, okay, this yellow thing is U, and we have a set A which is disjoint from U. So this is A. Suppose this is A. These two are disjoint. Okay. So this is A disjoint from U. And you know this X belongs to U. X is somewhere here. So X is somewhere here. Okay. Now, so this is okay. This is X. Now take complement of U. Okay, X minus U. Take X minus U. प्रतिभा बताएंगे X minus U कैसे सेट होगा?
Close set.
हेलो, हाँ,
Close set.
और X minus U is closed, and in this figure, what is X minus U? Let us draw that with a red color. Okay, so this part is X minus U. अच्छा, ऐसे कलर लाइन दूसरी बनाते हैं. This part is X minus U. Do you see where does this A lie? Where is A sitting? A कहां पर है अभी? प्रतिभा, प्रतिभा,
Yes, sir.
हाँ, A कहां पर है अभी हमारा? हमारे पास दो सेट है, U और X माइनस U. ओके, U एंड X माइनस U दो सेट है. A कहां पर है इन दोनों में? आपके पास फिगर दिया हुआ है.
Smallest closed. A.
A, अरे भैया, मैंने कहा आपके पास दो सेट है, एक X माइनस U है, एक U है. ओके, इन दोनों का यूनियन पूरा का पूरा X होगा. क्वेश्चन है A कहां पर है? A क्या U के अंदर है या X माइनस U के अंदर है? सेट
It's
A.
a X skin.
हाँ, अर्पित राज,
Yes, sir.
where is A sitting?
Sir, it is in X minus U.
It is in X minus U because U intersection A is empty, and in figure you can see it clearly. Okay, so this part is this is X minus U, and A is sitting here. This is A. Okay, this part is A. So A is inside U, and you said that this is closed. Okay, so X minus U is closed and it contains A. Okay, is this correct? And you know that closure of A in X is the smallest closed set containing A. This means this set is contained in X minus U because this is the smallest subset. Okay. So can you see from here? So because closure of X is somewhere here in the red part, okay, and X is in the blue part, sorry, yellow part. So this means X cannot be in closure of A in X. Okay. So this is what we wanted to prove. This is what we wanted to prove. So we are done. Okay. Now you can, so here we use open sets. You may replace this by basic elements. So base set. Okay. So you can say X in closure of X in A if and only, so closure of A in X if and only every base element or basis element. Sometimes you will see basic element, okay, B containing X intersects with A. So this is because you know every open set contains a basic element. Every open set contains a basis element because every open set is union of basic sets. Okay, basic set. So you have this. Good. So I left this as an exercise for you. So instead of basis element, you can replace this by neighborhoods. You can say every neighborhood of X intersects with A. Okay, X into A. If and only if every neighborhood of X contains a point of A. Okay, this means every neighborhood intersects with A. So let us see some examples of this kind. So take X equal to R and let Y be a subspace. Okay. So we are in usual topology. X in R with usual topology. Y equal to this set, this subset, which is open at 0 and closed at 1. This interval, semi-open interval. Okay, this is a subset, and in Y we are taking subspace topology. Now, take A equal to 0, half. Okay? A equal to 0, half. What is closure of A in X and what is closure of A in Y? So first, what is closure of A in X? Anurag? नेहा बहुत नेहा हेलो नेहा क्लोजर क्या होगा आवाज प्रीति सिंह प्रीति सरोज प्रतिभा रिजावत प्रतिभा क्या आप तक मेरी आवाज पहुंच रही है
Yes, sir.
हाँ बताइए तो इसमें इसका क्लोजर क्या होगा ए का क्लोजर एक्स में क्या होगा एक्स मींस यहाँ पर आर है एक्स इक्वल टू आर
The same
यूजुअल टोपोलॉजी हाँ किसी ने कुछ बोला so okay so suppose we take any point inside so हम जानते हैं a is a subset of closure of this so this means a के तो सारे पॉइंट वहां पर होंगे okay this means every point of a is in closure of so nothing to worry about it so what about other points say when we take point 0 okay now you have seen this a point belongs to closure if every neighborhood of that point contains a point of a okay so any neighborhood of 0 is of this form any neighborhood of 0 is of this form in usual topology when you intersect with a you will get 0 comma epsilon okay this is non-empty this means 0 belongs to closure a similarly if you take 1 okay if you take if you take half then a neighborhood containing half is of this form. Okay, when you intersect with A, you will get 1 by 2 minus epsilon comma 1 by 2. So this is again non-empty. Okay, so this means half also belongs to closure of R. So if you choose any real number x in R minus 1 comma 0 comma half, 0 comma half, okay, any interval, any point outside this closed interval, okay, then you must get by Archimedean, use Archimedean property, okay, you will definitely get an epsilon such that x minus x epsilon, x plus epsilon, when you intersect with 0 comma half, when you intersect this with 0 comma half, it is empty set. Okay, this means no point outside closed interval 0 comma half is in closure. This implies x cannot be in closure of A in R. So this means what is closure of A in R? This is the closed set 0 comma half. Okay, once we know this, then once we know this set, we will easily know this. So what is closure of A in Y? This is nothing but closure of A in X intersection Y. We know this is 0 comma half, and what is Y? See, Y is this semi-open interval 0 comma 1. So what it will be? It will be 0 comma half closed. So closure in Y is this set, closure in R is this set. See, both are not equal. Okay. So here I think it is enough for you. हेलो कुछ कौन बोल रहे हैं? हाँ नेहा कुछ कह रही हैं क्या आप? नेहा, निहारिका, आप कुछ बोल रही हैं? क्या आवाज नहीं आ रही? मैं आप मुझसे बाद में कांटेक्ट कर सकती हैं, मैं आगे बढ़ता हूँ, ठीक है? नेक्स्ट नोशन इज लिमिट पॉइंट. लिमिट पॉइंट. सो हाँ, क्या कह रहे हैं? हेलो
सर, ये क्लोजर. ओके सर.
कुछ नेहा कुछ बोला आपने? Okay, so now we will use, so in closure we have seen that every neighborhood of X contains a point of A. So what about this point X? If we do not take X, okay, in the intersection, and every neighborhood intersects A, and intersection is we get any other point other than, in intersection we are getting other points also, okay, other than X. So in this case we say those points are limit points. So let me write this. So we have a topological space. Let this be a topological space. Okay. let tau be a topological space, and we have a subset A of X, okay, and X in X be any point. We say that this X is the limit point of it, is a limit point of it. If every neighborhood of X contains a point, okay, of A other than X, okay. So this means if you are considering any arbitrary neighborhood U of X, okay, X in U, and you are taking intersection of U and A, and what you are doing, you are then not taking this X. This would be non-empty set, okay, or sometimes you can say a U intersection A minus X is non-empty. Okay, this is what you are saying here, and this is true for every such neighborhood. Okay, every neighborhood which contains X, not only one, every neighborhood. So let us see some examples. Okay. First, I will let me comment on the name. So in some books you will find cluster points, somewhere you will find accumulation points, so they are all equal. Okay, so other names for limit point are cluster point and accumulation point. Okay, then here is another definition: set of all limit points, of a set A is called the derived set of A, okay, and is denoted by A prime or A dash, okay. So
सर डीए से भी
set
डिनोट
of
किया
all
जाता
limit,
है
हाँ क्या
डीए
कह
से
रहे
भी डिनोट किया जाता है सर
या हाँ, उसको DA भी लिख सकते हैं, DA से भी डिनोट करते हैं, ठीक है। तो नोटेशन उतना इंपॉर्टेंट नहीं है जितना इंपॉर्टेंट कि इसका डेफिनेशन। तो नोटेशन आप बना सकते हैं जो भी है, लेकिन हाँ, दिस A dash इज स्टैंडर्ड नोट है। तो लेट अस सी सम एग्जांपल। अभी हमने एक सेट लिया था A इक्वल टू 0 का हाफ, okay. What is its derived set? What is derived set of A? What is A dash? अभी तो आप सब जानते हैं ये
सर
क्या
इट इज
होगा।
0 एंड हाफ
It is not only 0 and a half, it is closed set 0 and a half. Okay. So every point of A is a limit point. Why? Take any point. So देखो ये 0 का हाफ है, 0 था, ये हाफ है, इसके अंदर का कोई भी एक पॉइंट आप लें, ये वाला पॉइंट मान ले लेते हैं। जब आप इसको इंटरसेक्ट कराएंगे इसके एक नेबरहुड को, ओके, कोई भी एक नेबरहुड यू लीजिए, इसको जैसे भी आप इंटरसेक्ट कराएंगे तो ए के साथ इसका इंटरसेक्शन जब आप माइनस करने के बाद भी इनफाइनाइटली मेनी पॉइंट्स रहेंगे यहाँ पर, ठीक है। So make a puncture at this point x0, then you see this part, this green part is the intersection part, okay? This part, make a puncture at x0 and this part is the intersection. So any point of A is a limit point. However, so in addition to those points, this point 0 is also a limit point, because when you take a neighborhood containing 0, so you will get this form minus epsilon comma epsilon. So this means this part is the intersection part. Okay, similarly, when you take an open set or any neighborhood of half, any neighborhood, any kind of neighborhood, it will be of this form 1 by 2 minus epsilon 1 by 2 plus epsilon. When you intersect with A, you will get those many points, okay, infinitely many. So you remove this half, after removing, you have many points, okay, in the intersection. So therefore, half is the limit point. So this means A union 0 union half is the derived set, but this is nothing but closed interval 0 comma half. Okay, but so when you say A dash is this means you have to show that no other points are limit points. So this means if you choose points outside this set, so if you choose points here or here, okay, they are not limit points. So that is true. Take any point here, say this is the point. So you make a small neighborhood containing this, and it will disjoint from A. Okay, so do you get this? Is this okay?
Yes, sir. Please.
Okay. Now take x equal to R and another set, take B equal to 1 by n, where n belongs to Z plus. Okay. So this means this is this set. Okay. 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, and so on. So at this place we have 0. Okay. So what is limit point of this set? Okay, let us see whether
Sir,
1
0.
is a limit point or not. Let us see first whether 1 is a limit point or not. Take a neighborhood containing 1. Okay. So this is 1 minus epsilon, 1 plus epsilon. So you may always take such neighborhood. So we are not saying every neighborhood of A, we are saying there exists at least one neighborhood. So this neighborhood will intersect with B, but intersection point is only 1. When we remove this 1 from this intersection, we will get empty set. Okay? Correct or not? Hello? Similarly for this half, take a small neighborhood. So if you take a bigger neighborhood, or then this 1 by 3 will be there. But when we talk about limit point, we will take every neighborhood of A. So when we have to show that this is not a limit point, in that case we have to give at least one neighborhood which does not intersect with A minus X. Okay, so here this is the point half. Okay, take a small neighborhood half minus 1 by 10, half plus 1 by 10. Okay, or you may take even a smaller neighborhood, take 1 by 2 minus 1 by 100, 1 by 2 plus 1 by 100. When you intersect with B, you will get half only. But if you see the definition of limit point, we do not take this x, okay, we remove this. So what we do, we will remove this, okay, we will remove this. and in this case we will get empty set. Similarly, for 1 by 3, take a smaller neighborhood. For 1 by 4, 1 by 5, for every other 1 by n, we will get a smaller neighborhood such that this is true. But what about x equal to 0? So any neighborhood of 0 is of this form: x minus epsilon, x plus epsilon, where epsilon is positive. Okay, and you know by Archimedean property, for this for any positive number epsilon, for any positive real number epsilon, there exists a natural number or an integer, there exists a positive integer, and such that this epsilon is greater than 1 by n. Okay, this means x minus 1 by n, x plus 1 by n is contained in x minus epsilon, x plus epsilon. Okay, when you intersect this with b, you will get so many numbers: 1 by n plus 1, 1 by n plus 2, 1 by n plus 3, and so on. So there are infinitely many. Okay, so this 0 is a limit point of this set. 0 is a limit point of b. If you take any other real number, say this real number, it is not a limit point, because you will always get a neighborhood of this point which do not intersect with b. Okay, correct or not? So now another example. Take a set C union 1 comma 2. What is limit points of C? So this is of this form. So this is 1 point and then 1 comma 2. Okay, so I am denoting them by green color. So this is the set. This green is the set. Okay, so clearly 0 is not a limit point, because take minus half comma half. This is a neighborhood of 0. When you intersect with C and you remove the point 0, you will get empty set. Okay, correct or not? But when you take any other point in C, any other point, say this point, then this is a limit point, because take a smaller neighborhood. Okay, or take any neighborhood of this, it will always intersect with C. It will intersect in many points of C. Okay, with many points of C. So there are infinitely many. Similarly, this 1 is a limit point, 2 is also a limit point. You know how. So because if you take, say, consider this 2, you take a neighborhood of 2, it will always intersect with C. Okay? Any neighborhood of 2 will intersect with C other than the point 2. Similarly, any neighborhood of 1 will intersect with C. Okay, and there are infinitely many such points in the intersection. Therefore, 1 and 2 are also limit points of C. This means C dash, the derived set is nothing but 1 comma 2, the closed interval 1 comma 2. Okay, so now I am writing a theorem which is evident from the definition of limit point. Let x tau be topological space. A is a subset of x and x in x. Then The following are equivalent. The following are equivalent. Okay, means this is an if and only thing. X is a limit point of A, means X is in derived set. It is same as saying X is in the closure of A minus X. Okay. If you see the definition, it is evident from there. Okay, so I leave this as an exercise. Now, here is another. So in closure, so we define closure as the smallest set containing smallest closed set containing A. Okay, or we said that we take all closed sets that contains A and then we take intersection. So this is a huge task. Okay, to take all closed sets then find their intersection is the huge task. So how then? So if we want to deduce or we want to find closure of a set, then there is a nice way to do that. So what that nice way is this. You can see that nice way in this theorem. Let X be a topological space and A is a subset of X, then the closure of A is A union A dash. Means A union its derived set. Okay. So I'll leave this as an exercise for you. Please do this. I'll stop here. Any question? Any question? If there is no question, then I will leave the meeting. Okay, I will end the meeting.